Let's keep going on our exploration in the 4 different ways we can calculate a matrix product. Remember, in previous videos, we've seen how to do matrix multiplication via linear combinations of the columns. We've also seen how to do matrix multiplication via linear combinations in the rows. In this video, we're going to do matrix multiplication via dot products. Let's take a look at that definition. Here we go. We see the definition of matrix multiplication via dot products is given as starting with a matrix A, an element of Rm by P, and a matrix X, element of Rp by N. We say that the product B equals A times X is the M by N matrix whose individual entry in the ith row and kth column is given by B sub ik. And then this is going to be a quote-unquote dot product between row I of A and column K of X. So A is the left factor here, X is the right factor. And what we do is to find entry BIK, we take row I of A and dot it with column K of X. In colon notation, we say the ith row of A dotted with the kth row of X. This is true for I goes from 1 to M and K goes through 1 to N. Remember, however, this row vector, if A is an M by P, this is going to be a 1 by P. And then this column vector, if X is a P by N, this is going to be a P by 1. So a 1 by P times a P by 1. Formally speaking, that's not actually a dot product, right? We said that a dot product was a binary operation where the left and the right have the same exact dimensions. And in this case, the left has 1 by P, the right has P by 1. However, this goes back to one of our previous videos where we saw the matrix multiplication version of a dot product. This is equivalent to a dot product. So specifically, we say this is actually a matrix multiplication, but it's the same thing as if row I of A was a column vector, and then we dot that with column K of X, or the same way to say this is row I of A dotted with row K of X transpose. That's another way to say that, right? In any case, there's a lot going on in this definition. Remember, one of the things that I like to say is that when reading formal math definitions, one of the most important things we can do is actually do active reading, or what I like to call deep reading. In other words, get a paper and pencil out and deconstruct that definition at a very deep level to create a written record of everything that we're learning. This has 2 purposes. Number 1, it slows our exploration down, which means that we strengthen the neural networks in our brain because we go slower and go deeper. And then number 2, we're creating an external memory bank that we can use to come back and relive our learning for years into the future. Here I go in my own work. I'm going to go ahead and explore this matrix multiplication via dot products. We have A times X equals output B. Notice I'm not thinking about modeling matrix and algebraic worker. I'm just thinking about multiplying 2 matrices. And the reason I want to talk about that is when we want to find the individual entries of a matrix product using arithmetic, dot product can be very convenient. In other words, in this particular situation, we're not thinking about manipulating the columns or rows of A particularly. What we're trying to do is get the individual entries doing arithmetic. This version of matrix multiplication is super useful for doing calculations by hand, and also useful when we want to go down to the entry by entry version and kind of think about what the operations are down at that granular level. With that in mind, when we want to do matrix multiplication via dot products, what we're going to do is chop the left matrix into rows, the right matrix into columns, and the output into individual entries. Let's go ahead and do that. So in order to do the matrix multiplication via dot products, we chop the left matrix into rows, that's a row partition. We chop the right matrix into column, that's a column partition. We chop the right-hand side output into individual entries. Once we do that, we can do the dimension analysis on each of this. Remember, A was an M by P, which means the first row of A is a 1 by P. Second row of A is a 1 by P, all the way down to the bottom, which is a 1 by P, the mth row of A. Similarly, over here, X was a P by N, so that means this is a P by 1, P by 1, P by 1. On the right-hand side, each of these individual entries is a 1 by 1, and we can do something creative. Notice that a 1 by P times a P by 1 is a 1 by 1. Similarly, row 1 dotted with column 2, that's 1 by P, P by 1, 1 by 1. And in fact, we can kind of bring those together. So we take row 1, column 1, row 2, column 2, put it in entry 2, 1, all the way down to row M, column 1, put it in entry BM1, right? And that's exactly what we see here, right? Row 1, column 1, we combine them. Row 2, column 1. Similarly, we can move over to the second column. So if I want to B1, 2, row 1, column 2. If If I wanted B22, row 2, column 2, right? All the way down to the last entry, the mnth entry in our product, which is going to be row M, column N. Notice that the dimensions all work out. These things are quote unquote dot products, aka the matrix multiplication version of the dot product. The output of those is single entry, which means I have now a formula for each individual entry. Let's explore those formulas in depth and see if we can generate a pattern to get the general kth entry. We'll start with entry 1,1 on the right-hand side. So B11 is going to be row 1 of A dotted with column 1 of X. Let's go ahead and capture that. The entry of the first row, first column of the output B is going to be row 1 of the left matrix dotted with column 1 of the right matrix. But we know what that looks like, right? The left matrix is a M by P. The right matrix is a P by N, which means row 1 of the left matrix is going to be A1 colon, that's colon notation. Column 1 of the right matrix is going to be the first column of the right matrix. And then notice, since this is a 1 by P, we have A11, A12, all the way down to A1P. And then the column 1 of the right matrix is going to be X11, X21, all the way down to X1P. Once we have those written out, notice this is a matrix vector multiplication. We can do that by linear combinations of the columns, perhaps. So let's take the columns of this matrix. Those are individual scalars. And then let's scale those columns by the scalars in the column vector. So that's going to be X11 times A11 plus X21 times A21 plus XP1 times A1P. So here we've got a linear combination of the columns of this matrix. The columns are individual scalars. Another way to say that comes from thinking about commutativity. These are both scalar multiplication, so I can flip the order because real numbers are commutative. So this ends up being A11 X11 plus A12 X21 plus A1P XP1. But of course, this is a dot product between this vector as a column vector and that vector as a column vector. Notice that if I just kind of pair up the individual entries and sum up the products, that's a dot product, which is why we call this the dot product version of matrix multiplication. Moreover, we could write that using summation notation. Notice that the sum that we're looking at here starts at J goes from 1, and then 2, and then 3, all the way to P. So here we've got J from 1 to P of A1J XJ1. And we're wondering, how do these numbers 1 and 1 correlate with the row number and column number? So right now I see that A1 comes from the first row, so that has to do with this thing. And then XJ1, the 1 there comes from the first column, that has to do with this thing. And then we notice that the column index of the entries of A matches the row index of the entries of X, and that kind of makes sense because of the way that this multiplication works out, right? When I do this row vector times that column vector, what I do is I match each individual column of A with the appropriate rows of X, and so that's why the J's work out there. So notice what we've just said is that in order to get the entry of B in the first row and first column, I take row 1 of A, product with column 1 of X. Now, of course, row 1 of A is the same thing as column 1 of A transpose, and that's what we're talking about, the dot product, right? This is the matrix multiplication version of the dot product. This is the actual dot product. So, in other words, this dot product is between row 1 of A and column 1 of X. Let's keep exploring a little bit more. So here we go. When we did entry 1,1, we said row 1 of A, column 1 of X. Let's get entry 2,1. So let's get the entry right below that diagonal element. That's going to be row 2 of A times column 1 of X. Go ahead and finish this argument for yourself. Push pause. I've just given you kind of an outline. Of course, I'll do that with you. The point of this, though, is that to get your brain thinking and your brain working to do this. I'm trying to model this for you so you can kind of follow along my workflow. Let's do this together. So row 2 of A times column 1 of X. Here I've got row 2 of A. There's column 1 of X. In this case, instead of using the column vector version of matrix multiplication, let's use the row vector version. So let's think about these as the scalars and these as the rows. So here we go. When I take row vector matrix multiplication, I take the scalars from the row vector and multiply by each row of the matrix on the right hand side. Well, in this case, the rows are individual scalars, so that's kind of cool. So here, this A21 times X11 plus A22 times X21 plus A2P times XP1. So now all of a sudden I've got that multiplication. Of course, I could write that in summation notation. We notice that the column index of the entries of A aligns identically with the row index of the entries of X. That makes sense because I'm working across the columns of the rows of A and down the rows of the entries of X, right? And moreover, those are kind of correlated with each other. So that's why the J is in the column of the A values and the J's in the row of the X values. And then notice here that the reason that that number is 2 had to do with the fact that I was looking at row 2 of A. The reason that this number over here on the entries of X is 1 had to do with the fact that I was looking at column 1 of X. It is no coincidence that this is entry B21. It's in row 2, column 1, row 2, column 1, row 2, column 1. Let's go ahead and produce this. This is really nice, right? We just said that entry 2, 1 of our product is going to be row 2 of the left matrix times column 1 of the right matrix. Notice this is the quote-unquote dot product between row 2 of A and column 1 of X. When we say it's the quote-unquote dot product, we mean this is actually a matrix-matrix product, but it's equivalent to a dot product. What dot product is equivalent to? It's equivalent to looking at row 2 as a column vector, looking at column 1 as a column vector, and then literally taking the dot product between those two column vectors. When we look at row 2 of A as a column vector, that's equivalent to looking at column 2 of A transpose, since the columns of A transpose are equivalent to the rows of A transposed. And there's the dot product that we have. In other words, we're starting to generate that pattern. I can't help but ask us the question, are we ready to get the general pattern if I wanted to do entry IK? Do you have it? Go ahead and pause this video and see if you can make a guess about the general pattern. Go ahead. Do it. I know you can. On my end, generally, when I'm looking for a pattern and it's not evident, I like to do one extra. I think I'm pretty much ready right now, but let me do one more just to confirm my guess, and then I'll make it, right? In the absence of confidence, I'm willing to work a little bit harder to generate more intuition. Let's do that now. So here we go. We wanted to find entry 1, 2 of B. That means the entry in the first row, second column. Remember, we said that's going to be row 1 of A times column 2 of X. I'm going to go ahead and use some color coding to make this easier. So this is highlighted in orange and that's in blue. Let's go ahead and use the row and column operator notation. This is row 1 of A times column 2 of X. We could highlight those. So row 1 of A, we do the entry by entry version. This is A1, A1, 2, all the way down to A1P. I'm highlighting in orange to represent the idea that this is row 1, and that correlates with the entry number that I'm looking for. Similarly, over here, the entry in column 2, so that's column 2 of X. Here I've got X12, X22, all the way down to XP2. I'm highlighting that in blue to represent that we want the entry in column 2. In this case, maybe I'm ready to generalize and just say what I'm going to do is take the scalar in this entry, multiply by the first scalar, put it there. Scalar in this entry, multiply the second scalar, put it there. All the way down to the scalar in the last entry, multiply the last scalar, and put it there. This is equivalent to a dot product. I do like to be very clear with my students that this is the matrix-matrix multiplication of a dot product, because mathematics says formally a dot product has the same dimensions on either side, and we're violating that. However, this is an alternative mechanism to get that. So write that down in your notes, explore, ask questions, get excited about it. It's an important point from mathematics to be able to distinguish between the multiple operations that we're using. Okay, once we have this, we could of course create a summation notation. So this is the sum from J goes from 1 to P of A1J x J2. The 1 there is highlighted in orange since we're looking at row 1. The 2 is highlighted in blue since we're looking at column 2. The column index of the entries of A aligns identically with the row index of the entries of X. So that's the index J on our summation. And of course we say that this is the dot product between row 1 of A and column 2 of X. I could write those as column vectors if I wanted. So row 1 of A, here it is as a column vector, dotted with column 2 of X. Row 1 of A as a column vector is the same thing as saying column 1 of A transpose dotted with column 2 of X. That's an alternative mechanism to do this. The reason that I'm writing this in so many different ways goes along with one of my teaching philosophies that in order to do deep learning in mathematics, one of the best things we can do is explore multidimensionality, have many, many different ways to encode the same idea. From the standpoint of neuroscience, what we're doing is we're strengthening the neural networks in our brain by doing multiple dimensions. It's like distributing the entire knowledge over more parts of our brain, which means when we do the connections between the two of them, it creates a mesh that is much more robust and has larger sections of our brain lighting up. This is a great way to strengthen your math knowledge and make memories very, very sticky. With that, I think I'm actually ready to make a conjecture. Can we guess a pattern? I think we can. So I think that if I wanted to get the general ikth version, push pause, see if you can finish my sentence. What I'm about to say. I think it's going to be the ith column of A multiplied by the kth column of X. And one of the best ways to do this would be to stop looking at my paper for a second and say out loud what I think it's going to be. Then, after I've made that guess, go back to my paper and do all the hard work to confirm. Every error that I make is going to make that neural network stronger. True deliberate practice requires error and correction. And this is a great way to do this. You'll notice that if you actually follow my directions, you get tired, at least I do, right around the 2 or 3 hour mark, and I need a break because I'm working so hard. The point is not to passively consume math, it's to actively construct math, to push yourself past your limits and to construct new knowledge. Let's go ahead and do that. Remember, after you do it out loud or in the air, write it down. You're creating a library of resources that can last for the rest of your life if you want to refer back to this, right? So we're saying that the kth value of the output is going to be the ith column of A multiplied by the kth column of X. So that's row 1 of A multiplied by column K of X. Of course, when I write this down, I've highlighted I in orange and K in blue, which means that the row index in all of these entries is going to be I orange. The column index in all of these entries is going to be K blue. So now when I take this product, I take first times first plus second times second plus plus pth times pth, and that leads to the sum AI1 x1k plus AI2 x2k plus AIP xpk, which we can write in summation notation. J goes from 1 to p. The row index on the entries of A correlates with the row index of the output that I want. The column index on the entries of X correlates with the column index of the output that I want. The column index of the entries of A align with the row index of the entries of X, and that makes sense because of the way we're doing this product, right? We're aligning the corresponding entries in the columns of A with the rows of the columns of X. That checks out from the matrix-matrix multiplication via linear combinations of columns and linear combinations of rows. That's one of the whole points in all those pieces, right? Do you see me describing these in multiple ways verbally and also making connections between old ideas and new ideas? Deep learning in mathematics, you see it? All right, let me put a nail in this coffin. This is the dot product between row I of A and column K of X. Of course, I could write row A of I as a column vector. Here it is, column K as a column vector. When I take the dot product of those, I get the output that I want. When I look at row I of A as a column vector, that's the same thing as saying column I of A transpose, since the columns of the transposes are the rows of the original matrix transposed. And we have yet another way to think about this. With that, we've covered our first introduction to the matrix multiplication via dot products. Remember, the intuition that I'm trying to help you generate is that we use this version when we want to find individual scalars or individual entries of the right-hand side output matrix. We're not thinking about modeling matrix and algebraic workers per se. We're literally thinking, I want to multiply two matrices and I want to get entry IK. How do I do that quickly? This is super useful if you're going to take math exams in a time pressure situation. It's a good way to focus on each individual entry. There are also some situations in application areas and computer science where you might want to rely on these. We'll talk about those in my MATLAB video series. This leads very nicely into the community challenge for this video. Make a quote-unquote cheat sheet for yourself of all the similarities and differences between the 3 versions of matrix multiplication that we've done. Matrix-matrix multiplication via linear combination of column vectors, matrix-matrix multiplication via linear combination of row vectors, and matrix-matrix multiplication via dot products. We're going to do yet a 4th version in future videos, which relies on something called an outer product. We've seen that in the past. For now, get started on really making the interconnections, compare and contrast. When do we use one version? When do we use the other version? What are the formulas? What are the similarities? What are the differences? I can give you an example of this. Matrix-matrix multiplication via linear combination of columns, I cut everything into columns. Linear combination of rows, I cut everything into rows. If I want to do dot products, I cut the left into rows, the right into columns, and this one over here, I cut into individual entries. That's just a few examples. I could go on and on and on. For students in my class, I don't think about this as a cheat sheet. You are not given timed exams. I will never grade you on a timed basis. I think that your genius shines greatest when you can think slowly and deeply. And I feel that any resource that you use, you should have access to at any point. I'm going to be honest with you. I would fail most times exams in a math class right now, because I refuse to work under time. I've been getting paid to do math for about 18 years. If a teacher gave me a timed exam, I would refuse to answer it. I would literally give it in blank, even though There is almost no math on this earth that I can't learn by myself. Of course, you see all the books behind me. I use authors to guide my work. And that's what all mathematicians do at some level. We read each other's work, we think critically about it, we construct new knowledge, etc., etc. I don't see why we should change that structure in classes by doing timed exams when we don't even do that in our own life. Most mathematicians think 5, 10, 15 hours about a particular idea before we've decided whether or not we understand it, right? So I think that you should have the same privileges in my class, and I structure my class accordingly. So what I want to say is any work that you do is not a cheat sheet, it's a learning resource. If you do it well, you can reference this for years into the future. Remember, the work that you produce in this class is not for me, it's for you. My goal is to empower you to figure out how to use linear algebra as a tool for transforming your communities. I think that there's a bunch of linear algebra applications and ideas that have yet to be discovered, and I believe you can be one of a new generation of scientists to discover those applications and create new ideas. This class is designed to empower you to do that. I'll shut up now. In the next video, we're going to take a look at an example of how to use this. I thank you so much for your attention. Please go ahead and provide comments, feedback, questions in the links below, and I'll see you in that next video.